So thermodynamics, or thermochemistry, as it is at school, is about the business of how energy changes when you do a chemical reaction. And you have to kind of understand what energy means, and we're going to try and define that a little bit. But it's something that you kind of know about. I mentioned the Hindenburg the other day. Here's a picture of the Hindenburg. In fact, it was 1937, and it was at Lakehurst Naval Air Station, although I still don't know where that is, but that's okay. It's in the States somewhere. And so obviously when that chemical reaction happened, there were some energy changes going on, yeah, because there was a huge fireball. And you know about this, the chemical reaction, I mean obviously the chemical reactions that go on in your body are in part to keep you warm. They release energy which keeps you warm. When you drive around in your car, the engine gets hot because the chemical reactions involving the petrol when the engine goes release heat and make your engine hot. Okay? Chemical reactions involve energy changes. Thermodynamics is about trying to measure and understand those energy changes. And it can be desperately, horribly complicated, and we're not going to get very far into it, but it is the first subject you're going to do in Chem 191. So pretty much right from the first day, you're going to be doing this stuff. So we know from our experience that when chemical reactions occur, heat can be given out. That when some chemical reactions occur, heat's given out. So in other words, so for example, petrol reacting with oxygen in your car's engine. Your car gets hot. If you don't have an efficient cooling system, your car overheats and it stops, right? Lots of heat is given out. And so we have a name for these sorts of reactions, ones where heat is given out. We call these exothermic reactions. Okay, so therm is like thermal underwear. It's a word that is to do with heat. And exo is like exiting. So an exothermic reaction is one where heat leaves the reaction. So if it's happening in a beaker in your hand gets hot because the heat is leaving the reaction and going into your hand and making it hot. Yeah? And so exothermic reactions are pretty common, and you know, a lot of the chemical reactions you see, you know, the sun working is an exothermic reaction, right? Less common are reactions which absorb heat when they happen. In fact, they're still quite common, but they're a bit more subtle and you have to think about them. One example would be ice packs that you have for sports injuries. So if you're one of these people who runs around in a field on the weekend and you do your knees in and you sit on the side and they've got these big things they scrunch up and put on your knees to cool them down, when you scrunch them up, that starts a chemical reaction happening, and that chemical reaction absorbs heat. So it sucks the heat out of your knee and into the reaction, and by doing so stops the swelling or whatever in your knee, right? So that's a chemical reaction that absorbs heat. Even if you just put ice on your knee, then what will happen is that the ice will melt. And the process of the ice melting is an endothermic process. It requires heat. And so when you put the ice on your knee, it will suck the heat out of your knee, and that energy will be used to melt the ice. Right? So ice turning into water, which is a process which, if you're not from Dunedin, you will soon find is a very common chemical reaction around here, is an endothermic process. Water evaporating, same deal. The reason why you sweat when you get hot is because the liquid water turning into water vapor is an endothermic process, and so you sweat and you get all wet on the outside, and then as that evaporates, it takes heat, so it sucks heat out of your skin and cools you down. Yeah? So these are quite common things, but they're a bit more subtle. You don't think about them the same. These sorts of reactions are called endothermic reactions, right? So endo meaning going in. So the heat goes into the reaction when it happens. Right? So exothermic reactions that release heat, endothermic reactions, ones that absorb heat. And so the science of thermodynamics is concerned with these sorts of energy changes. And in the cases that we're going to be looking at, this energy will be in the form of heat. This is all you really do at school. Here is you look at energy changes in terms of heat. There are other sorts of energy changes that happen. If you think about the Hindenburg, then when the Hindenburg went bang, there was a lot of heat given out, yeah? But there was also a lot of light given out as that reaction happened, right? Because when things burn, they give off light. That's a type of energy change. Initially, there was no light being given out, then all of a sudden there was. There would have been a bang. That's another type of energy change, right? So there's various different types of energy changes that can happen when a reaction occurs. But the easiest one for us to measure is the heat change. And so that tends to be the thing that we start with, and then we go on and look at the more subtle things later on. This is what you're going to do at the start of Chem 191. But for the moment, we're going to focus on heat changes because they're easy to measure experimentally. And then, of course, there's another subtlety, which is that there's different types of heat. And this is a much more subtle definition, and it's very old man with a beard, physical sciencey type thing. But what we're going to be talking about specifically is the heat change that occurs when a reaction or process occurs under constant pressure. And what that really means in reality is doing chemical reactions in beakers and mugs and things like this with the top off. Because what we assume is that the pressure that's impinging upon that reaction is just atmospheric pressure, and we assume that that's not going to change significantly over the course of your reaction. If you were to do a reaction with a lid on and the whole thing sealed up, that would be different, because if the reaction made a gas and then the gas started building up, then the pressure would increase. And so that would be a different thing. Those of you who are maybe planning on doing human nutrition and dietetics and that sorts of things, you'll be talking a lot about that sort of heat change in those courses, because the type of heat change that you use when you're measuring things like the energy values of foods is talking about that sort of process. But for now, for the chemistry, we're going to be talking about processes in beakers with the tops off, right? If we're doing that, then we give the heat another fancy name, and we call it enthalpy. Right? So enthalpy is just another way of saying heat, so long as you're talking about heat in a reaction under conditions of constant pressure, i.e. with the lid off. Yeah? When the reaction happens, you start off with your reactants and then you mix them together and the reaction happens and heat is either released if it's an exothermic reaction or heat is absorbed if it's an endothermic reaction. And what we can do experimentally is we can measure the change in the enthalpy. Right? How much is given out, how much is taken in. There's all sorts of interesting philosophical reasons why we can't measure the total enthalpy of your reactants before you start, and we can't measure the total enthalpy of the products when you're finished, but you can very easily measure the change in enthalpy on going from the reactants to the products. And so we're going to be all about talking about changes in enthalpy, and the symbol we give for change in enthalpy is this one here. The big capital H is the symbol for enthalpy, and the triangle in front, delta, is meaning the change. Right? So that triangle, the delta H, is the change in enthalpy that occurs when your reaction happens. Yeah? Now, what I want to do is just flick, 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 flick. Oh, there we go. We'll get to there, at least. There are various different types of chemical reaction that we can measure the enthalpy change for. And some of them are common enough they get their own fancy little names. And so one of them is this. We can talk about something called the standard enthalpy of formation. And this is the enthalpy change under a certain set of conditions for a particular type of reaction. It is the reaction that involves making some compound, and it can be anything you like, but making that compound from its constituent elements in their standard states. And that, dare I say it, is a definition that probably is worth remembering because we do often ask you this sort of thing. So the enthalpy of formation is the enthalpy change that occurs when you make 1 mole of a compound from its constituent elements in their standard states. I haven't told you what standard states means yet, but that's the definition, right? And so here is an example of an equation like that. Where's my stick? So this would be the formation reaction, as it's called, for carbon dioxide, CO2 gas, right? And so we look at our CO2 gas molecule and we see that it's made up of carbon and oxygen. So if we're writing a formation reaction, then the reactants have to be carbon and oxygen, right? It can't be CO plus an O, or it can't be CO3 minus an O. It has to be carbon and oxygen reacting to make CO2, right? To be a formation reaction by this definition. And what's more, the balancing has to be such that we've only got one of these as a product. So that will mean that sometimes you'll have to have fractions here in the balancing, but that's okay. It's just the way it has to be. And it has to be that the carbon and the oxygen are in what we call their standard states. Now, standard states are something that you can have a fancy definition for, but basically it just means if you were to go home tonight and bump into some of that element on the street, what would it look like? Right? So you kind of know that carbon is a solid, yeah? So carbon in its standard state is a solid. You know that oxygen is a gas. So that oxygen in its standard state is a gas. So we have carbon as a solid plus oxygen as a gas gives 1 mole of CO2 gas. Right? So that would be the appropriate formation reaction equation for making CO2. If this was O2 liquid, it would be no good. If this was carbon as a gas, it would be no good. Right? Standard states, the way that you would see them on the way home. And then you could say to me, oh, but I don't know about germanium. It doesn't matter. We're not going to ask you about germanium, right? We're going to ask you about things you know. Carbon, sulfur, oxygen, nitrogen. These ones that you kind of have a feel for, hopefully, yeah? If not, go home and learn all those videos, because there's pictures of them all, yeah? For a reaction like this, if we can measure the enthalpy change, then we give that a name and we call that the standard enthalpy of formation. And so now the symbol here gets a little bit more complicated. Here's our delta for change. Here's our H for enthalpy. Down here we have a little F. That means formation. We're going to see other versions of the F as we go along, but for the moment, delta F, H, and then the wee superscript circle means standard. Sometimes you might see this written like this. Have we seen this? Some people? Yeah, the circle with the line through it. Again, it kind of depends on what textbook you read. The way we teach it here doesn't have the line, right? So this is delta FH standard, the standard enthalpy standard enthalpy of formation for this reaction, right? So if you can measure how much heat's given out in that reaction or how much heat's taken in, then that will be this delta FH standard thing. Right? Last slide. The value of delta FH standard for a particular formation reaction reflects the difference in energy between the reactants and the products. Okay? Or if you like, more specifically in this case, the difference in enthalpy between the reactants and the products. And these differences are there because the reactants and the products will have different sorts of chemical bonds. And different sorts of chemical bonds inherently have different energies, different strengths, if you like. So when we do a chemical reaction, we're breaking some bonds and we're making some new ones. And at the end of the day, that might require some extra energy to make the bonds, or it might mean there's some energy left over because you've made a bunch of bonds that didn't need so much energy as what you started with. Yeah? And so we could draw some little pictures that look like this, little graph things, right? And so obviously there's two options. Here's one of them. This would be the option if, so here's enthalpy up the y-axis, and here's something that doesn't matter along the x-axis. But here's our reactants up here with a certain enthalpy in them that we can't really measure, but it doesn't matter. And here's our products down here with a different enthalpy, which we can't measure, but it doesn't matter. The key thing here is that when we go from reactants to products, the enthalpy in the reactants is bigger than the enthalpy in the products. So when the reaction happens, and we go from here down to here, we have energy left over. We have enthalpy left over, right? So this would be an exothermic reaction. When we come to work out mathematically what the value for the enthalpy of formation is for this reaction, what we do is we take the enthalpy of the products and we subtract from it the enthalpy of the reactants. Okay, at least on paper that's what you would do. The point I'm trying to make here is that it's always the final thing minus the initial thing. So whatever it is at the end, you subtract off that what it was that you started with. Now the point is that for this sort of arrangement, where the reactants have higher enthalpy than the products, the value you get for the enthalpy change will be negative. It'll be a negative number. Yeah?
How do you know what products or reactants have more enthalpy?
Because what you will do in reality is you will look for the sign on the value for the delta H that we give you. Right? If the delta H is negative, that means the products must have had less enthalpy than the reactants. And so you get a negative value for delta H if you're an exothermic reaction. Yeah? The other option, obviously, hopefully, was this one, where the reactants have less energy than the products. And so in order to go from reactants to products, you have to get some more energy from somewhere else to get up that hill. And so that's why if you have one of these reactions happening in your hand gets cold, because the reaction sucks the heat out of your hand in order to turn its reactants up into products. So here, the delta H will be the enthalpy of the products minus the enthalpy of the reactants, and that will be a positive value in this case. And so that's what you expect for an endothermic reaction. An endothermic reaction will have a delta H value that's positive, whereas an exothermic reaction will have a delta H value which is negative. So the key things here are this relationship between exothermic and negative delta H, endothermic and positive delta H, but also, because we're going to come back to this sort of underlying idea a lot, the fact that the change is the final thing minus the initial thing. Right? We're going to do that a lot, not just in thermochemistry, but in other parts of chemistry as well. The delta always means final minus initial.